I'm going to kick this off. So in February, as you probably remember, we had a presentation from Dr. Meredith McCormick from Johns Hopkins University about the health impacts of air pollution, particularly particulate pollution, PM 2.5. So to follow up on that and to prepare for the visit to the ORCAA monitoring station in Lacey this afternoon that many of you will join us on, Odelle's put together a presentation about how we measure atmospheric particles.
Great.
Odelle.
Thanks, Jeff. Dan, could you please put the presentation on? All right. Thanks for all being here and entertaining me while I talk to you for a little while. So particulate matter or atmospheric particles is one of 6 criteria pollutants that EPA has set standards for, but it is unique among those pollutants because it's the only one that's based on physical properties rather than chemical properties. All the other criteria pollutants are one compound, like ozone, SO2, sulfur dioxide, carbon monoxide, so gases, or even lead, which shows up in particles but is one element or molecule. So first, I'm going to talk a little bit about those physical properties. So particulate matter, it's really important to think about size, and a lot of people don't think about sizes this small. So I'm going to be talking about micrometers, which are also equal to microns. Those are used interchangeably because scientists love to have multiple ways to say things. The abbreviation for micrometers is that μm, so you'll see that in the units. And for those of you that don't know, that is equal to 1/1,000,000th of a meter. Or if you look at the picture here, there's a picture of a human hair, which the diameter of a human hair is about 50 to 70 micrometers. And particulate matter, which is classified by size, you'll see the PM10 is the blue dot, and about 5 of those will make up a human hair. We go even smaller to PM 2.5, which is what I talk about all the time and what you'll hear me talk about most during this presentation, and that makes up about 5 going across, or 4, I'm sorry, going across for a PM10. And then you'll even hear sometimes people talk about ultrafines, where the diameter of an ultrafine is equal to 0.1 micrometers or 100 nanometers or less. And so that just gives you an idea of how small particles we're talking about here. We aren't going to talk too much about ultrafines after this because they don't have a lot of mass, and most of what we're looking at is the mass of the particles. They do have a high number concentration, and there is scientific evidence that shows they do impact, they penetrate the furthest into our bodies, and so they have a high health impact, but they don't have a very long atmospheric lifetime, and they are difficult and expensive to measure. And because they don't have a long atmospheric lifetime, it's been difficult to correlate them and really come up with a health risk associated with them that is based on ambient concentrations rather than laboratory studies. So we are going to just stick to PM10 and PM 2.5 for this presentation. So the next plot, some examples of atmospheric particulate matter. I mentioned it was based on physical properties, and it is composed of thousands of different chemical compounds. So here's just an example. You'll see the little scale down in each picture. It changes. So the top one is dust, which is 1, and that little white bar is 1 micron. So you can see how small that really is. We also have iron composition, which can be part of dust. Quartz, again, part of dust. Some different ones. Fly ash is an interesting one because that is one that we generate here in our area from different industrial sources. You'll see it's very spherical. I was curious about why it was so spherical, and that's where you get molten metals coming out that are almost gasified, and then they recondense as the stream cools and form these little tiny spherical glass-like particles. Also want to point out soot, also known as black carbon, down there in the lower left. And then salt can be a big one near the ocean. So just an example of some different types of chemicals that make up PM2.5.
Pollen, there's a lot of that in the air these days.
The pollen's a fun one, and that's 5 microns. So that's interesting. Pollen's pretty big. It doesn't actually make it very far into our system. So if you have an allergy, you're mostly going to feel it right here in your nose, right here in your eyes, and right here in your throat, because it's so big it doesn't really get much further than that into your airways. So I just want to point out that next slide, please, Dan. the chemical composition of PM 2.5 isn't the same. And so here's just kind of a general broad view of different chemical components that make up the majority of PM 2.5 across the country. And I just really want to point out in the Northwest, in our region, there's a lot of that gray, which is carbon. That's organic carbon and black carbon, and typically comes from combustion sources. So the majority of our PM 2.5 PM is from combustion sources in our region. You'll see in other areas, there's a lot of sulfates, a lot of nitrates, and even a little bit of crustal, which is another way to say dust. And so the nitrates are a lot of agricultural will generate that. Sulfates can be from shipping or diesel exhaust. So just everybody kind of has their own unique blend of what makes up PM 2.5. And then next slide, please, Dan. So this improved network dates back to the 80s. This is sites that collect PM 2.5 on filters and analyze them for their chemical composition. And so these sites that you'll see are what that previous slide was generated from. So we have been measuring the chemical composition of PM 2.5 for a really long time. And I just want to point out that if you look way up in the upper left-hand corner, you'll see ORCAA. That little blue dot is the improved site that's co-located with our NCORE site that I've talked about. It used to be Chica Peak, it's now Pocos Peak. And so we are getting chemical composition from up there as well. And I did publish a paper many years ago now, I think almost 9. Next slide, sorry, Dan. Where I use that improved data to determine what our primary sources of PM 2.5 were at the site. And so what we found was ships, especially in the summer. Wood smoke was a big one in the winter. Sea salt was another winter one. Dust showed up in the spring. And then we had sort of this mixed background aged particles that were just kind of there all year round. If you want more information on how I did this and the actual components, just let me know and I can give you a copy of that paper. So let's get.
May I have a question?
Yes, of course.
The ships, are those out at sea or are they in port?
Those are the ships that are coming up the coast and going down the Strait of Juan, probably. I mean, they could be some from in port too, but mostly we see that in the summer, and the wind direction is favorable to that strait. That northwesterly wind direction indicates ships out at sea.
Great, thank you.
Okay, so how do we measure particulate matter? Well, we've talked about size. So size, the first step is to isolate the size that we're interested in. Back in the late 80s, early 90s, PM10 was the primary one. And so we used that top inlet there, which is a PM10 cyclone. You'll see an inside view of it on the left, pointing to where that would correspond in that inlet piece. You're going to see that inlet later this afternoon out at the Lacey site. So all the particles go in the top. There's a screen up there that keeps bugs and stuff out. You'll see a water trap off the side. It's a little jar. Any water or moisture in the air streams that get in there get accelerated down there and thrown out the side into that water trap. So we don't want to measure water. We want to make sure we're not measuring water when we look at these particles. So you'll see in that left-hand side, the particles come down, and anything larger than 10 microns goes straight down. It's too big to make that turn around those edges, and it just hits that plate and it gets trapped there. And so that all stays there. And then all the stuff less than PM10 go around the edges and keep going down to the next size cut stage, which is that little very sharp cut cyclone you'll see further down. And so there, anything larger than 2.5 microns bends and goes down to that impactor plate, and everything else that is smaller than that can make it around that final bend. And so only particles smaller than 2.5 microns can make it into your reaction chamber, whatever that may be. So next slide then. So the first method that I'm going to talk about is the gold standard. So the federal reference method. This is a weight-based measurement. It is a direct measurement of particulate matter. So it's a mass per unit of air, usually meter cubed of air or volume of air. It starts in the laboratory. The filters are put into this chamber and conditioned at a specific relative humidity, pressure, and temperature for several days. They are weighed, they are numbered, identified, and then shipped out to the field operator, who then installs them into the sampler. And so there's a pump in there, the pump pulls at a very precise flow rate through that filter. The way that we check that, the operators regularly have to go out and verify the flow, verify the temperature, verify the pressure that that instrument is giving, so that we know all those parameters are accurate. And then those filters you'll see in the bottom, the two tubes. So the filters are in one tube, and then they cycle through the sampler and get collected in that other empty tube on the other side. So once a week, operators go out, pick up those filters, and ship them back to the lab. The filters collect for 24 hours, so you get a total just average mass per 24 hours. And then they get back to the lab. Once they get back to the lab, they get back into the chamber, where they are put at the exact same relative humidity, pressure, and temperature that they were conditioned at, because that can affect the weight. And then they are weighed, and then the difference in the weight is the mass of. So it's a very simple idea, but it's a complicated process. So the pros and cons: it's the most accurate method. And we can use those filters and analyze them for chemical composition later, so we get more than just the PM 2.5 concentration. There are the least interferences with that, so the measurements are not biased, and it provides validation for lower cost methods. But there are some cons to it. You only get a 24-hour average. You don't get to see what's happening hour by hour or minute by minute. The data are only collected once every 3 or 6 days, so you might miss a lot of days. It's really just kind of trying to assess if we're in an attainment. And those data are not available for weeks. So if there's a bad PM 2.5, smoke episode, this data is not going to pick it up or tell you that. There are some issues. Some evaporation in the field on hot days can reduce the measured mass. And as you can imagine, because you have a lab component and field component, it's expensive and time consuming to operate. So there's a lot of the data aren't super usable in real time, and they're really costly to do this. So let's talk about federal equivalence methods. So these are methods, there's a lot of them. I'm only going to talk about the one we have here at Lacey, but these are methods that EPA has determined to be equivalent to the federal reference method. And in most cases, you can actually get better real time. So the one that we have at Lacey is an FEM. It's called a beta attenuation monitor. I talk about it a lot. Rob loves saying BAM really loudly. Basically, it collects particles on a filter every hour, and there's a carbon-14 source that's emitting beta radiation through that filter. And the number or the mass of particles on that filter absorb beta radiation. So if it's a blank filter, the detector measures 0, and as it accumulates more mass on it, that detector signal for the beta radiation will decrease, and that will give us the mass of particles on the filter. And you can see down there the tape. I have a picture of the tape that's going through that. The different colors just kind of are indicative of how much particulate is on that filter. So how does the federal equivalence method, in this case RBAM, compare to an RM or a federal reference method? And these data were from 2023 and 2024, collected at the Beacon Hill site in Seattle, where they are still running an FRM and a BAM at the same time. And you can see that on most days they agree really, really well. Where the red arrows are, you'll see that there are days when they don't agree, and there's lots of reasons for that. Operator error, the filter got ripped, something happened where the BAM wasn't, working properly that day. So that does happen, but by and large, those two monitors are measuring the same thing. Next slide, Dan. So the beta attenuation monitor is great. It gives you near real-time data. It's not dependent on chemical composition. It's low maintenance and a high percentage of valid data, or the juice is worth the squeeze, I guess. I don't know. And you get the daily average data are validated against federal reference methods. So it really is a robust method for measuring PM 2.5. There are some cons. If it's really humid or there's a lot of background radon radiation that can cause interferences. And then the hourly data are noisy in clean environments. And so if you're looking at just the hourly data, it's great when you get up above into the moderate or the unhealthy for sensitive groups. But when it's really clean, it tends to be kind of noisy. So now I'm going to go to the most common way we use to measure PM 2.5 at all of our sites. Also, we have one co-located with the BAM at Lacey, but this is the nephelometer. It's based on light scattering. So little teeny tiny particles will scatter light. You see this when you walk into a dusty room and there's like a sunbeam coming through the window and you can see the dust in the air, and that's essentially how this works. So if it's very clean, no light gets scattered down to that detector. So you'll see all those little lines coming across, those are like baffles or traps. The inside of the nephelometer is painted flat matte black. So it literally absorbs all the light that does not get scattered to that detector. So this is kind of like the opposite. The more particles you have in that chamber, the more the detector sees, the more light the detector sees. So it's opposite of the BAM where we're reducing the signal based on PM 2.5. And this one, we're actually increasing the signal with the more PM 2.5 we get. I did say that particles scatter light, they also absorb light. So if you have like black soot or black carbon, which I'm going to talk about in a minute, this instrument doesn't see it very well because it's just absorbing that light like the walls, not scattering it to the detector. So pros and cons. The nephelometer, it provides real-time data. In fact, we can get minute data that are actually pretty accurate, whereas the BAM only gives us hourly. So if we have a smoke cloud roll in, I know it within 5 or 10 minutes. I'm like, uh-oh, this thing just skyrocketed. We got a problem. It is very low maintenance. We can do quality checks on that signal and make sure that it's operating the way that we expect it to. And we do get a high percentage of valid data, and the data are stable even at very clean environments. So that's nice. If you do have high humidity, that can cause higher measurements. We get around that by heating the airstream. So we drive the humidity down and just dry all the particles out before we measure them. And as I mentioned, composition can change light scattering efficiency. So if you have a lot of particles that are black or dark or absorbing light, that's going to scatter the light differently. So there are some high uncertainties based on that because we don't necessarily know the chemical composition. These data are not regulatory, so we can't use these data to say we are in attainment or that we're meeting max. But what they do for us is if we get to within 80% of the National Ambient Air Quality Standard, then, and we have a certain number of population that this represents, we could be required to install an FEM. So they kind of help us know that we're meeting standards, and if we're getting within that we might not be, then we would have to install a more expensive monitor there. The other thing is they can't detect particles below 0.3 microns or micrometers. That's because particles scatter light at the same wavelength, where the wavelength size is about the same as the diameter, and 300 nanometers is getting into the ultraviolet, not visible light range. So those ultrafines, the nephelometer can't see them. Okay, so, and then finally, low cost air sensors. This is the newest thing on the market. They have a high uncertainty, but look at how many there are. So this is from the EPA's fire and smoke map, which takes purple air sensors, our air monitors, clarity nodes, and even the state sensors, the SenseWAS, and just combines them all on one map. So the big circles are the official monitors that I have just been talking about that are state or local or even EPA run monitors. And then all the little dots could just be any citizen's sensor that they've installed.
Or the one outside that
or the
door.
one outside. See this little line going up here? We have one installed outside our door. So they do have high uncertainties, but in great numbers, they are very useful. Here's a next slide, Dan. These are, this is an example of how many we've got here in Washington State. And you can see the clusters in the big cities. Of course, people like to install those, but it's sort of a citizen science collaboration that's happening with government, which is just great. Next slide. So talked about the pros. They're very low maintenance. They do have a stable data signal. They're low cost. Purple Air's run you about $300 as opposed to $2,000 to $10,000 to $30,000 for some of the better ones. Because the members of the public are able to buy them, we can crowdsource the data, we can empower citizens. It didn't used to be possible for a citizen to buy their own air monitor, now it is. I mean, I get that 300 is still a lot for a lot of people, but it's now within range also of a lot of private people. Some of the cons, though, there's a high positive bias. The accuracy of these monitors change a lot. So there has to be a lot of validation done on the data. So we use correction factors and those change depending on the location and ambient conditions. We do have high uncertainties for any individual monitor, but again, when you have a huge number of them, that can go down. We don't have any way to verify them and make sure that they're not malfunctioning. So typically it's just, oh, it doesn't look anything like its neighbors. Maybe it's not accurate. So the next slide. So how do they compare? So now I'm comparing the BAM or the FEM, which is the dark blue line, with the nephelometer, which is the light scatter technique. That's the yellow line, with the purple air, which is the purple line there in the data. And here's where you can see where that BAM data are noisy in clean environments. And those other two, the light scatter data, are a lot more stable. But when we do see the high peaks, all three sensors agree pretty well. And we can see that they're in general going up and down at the same, picking up the same peaks, picking up the same concentration of PM 2.5. The only time we really start to see problems is when we get down below 5 micrograms per meter cubed, and that BAM kind of is dropping down into the negative numbers and the positive numbers. But at that level, we're not that concerned. We just say it's clean. The air is good, so not as big of an issue. If we take the daily averages, as if we were going to compare to an FRM, you can see that that noise really just kind of goes away and that the monitors mostly agree with each other on a daily or 24-hour average. And so the last thing I'm going to talk about is the light absorbing measurements. You're going to see this over at the Lacey site too. This is our ethylometer. So this kind of makes up for where our nephelometer can't see black carbon or soot. This is our method to say we can measure it and add that in as well. So, and this actually helps us determine where the combustion sources are coming from. And that's because diesel and oil produce a very black smoke. And that the ethylometer has different wavelengths of light. So it has red light, it has green light, it has blue light, and wood smoke, especially low temperature wood smoke, appears to be more brown or reddish, and that's because it's absorbing all the blue light more, whereas the black soot absorbs all the light equally, and that's why it looks black. And so here's an example of what those filter spots look like depending on what we're measuring. So black carbon at the top, kind of a mix in the middle, and then like low temperature wood combustion where it's very orangey, yellow, brown colored in the bottom. And that's what this data, next slide, please. That's what the data look like from the ethylometer, where you have the two different wavelengths of light. So where there's a lot of organic carbon that is red or brown, you see that the spikes in the yellow are almost twice that of the black soot one, or where they're about the same size, that indicates more of like a diesel particulate or oil burning or something like that. Next slide. And you can see that with your naked eye when you go out and look at smoke. So this is two examples of different fuels for combustion. The left-hand side was actually a violation notice. We had a hog fuel boiler that had some wet.
Fuel and some diesel to supplement the wet fuel.
Yeah, they put diesel in their hog fuel boiler, which they were not supposed to do. And we got complaints on this big black cloud coming out of it. So that's a picture Mike took.
How'd you catch that, just out of curiosity though?
What?
Complaints.
Complaints. People lived up on the hill and they saw it and they knew to call us.
And you happened to go there and be able to do it while they were doing it?
I went there and they were still doing it. It was still happening. In this case, I happened to be in the Grays Harbor area, in the area anyway. And so I didn't take
We
that
do
long
like that
to go.
in Mason County too, don't worry.
Yeah. So yeah.
Wow. Impressive.
And then the other one, you can see smoke from a wood pile that someone's burning, and when you look up and you can see that orange red color that, and even when we have wildfire smoke episodes and the whole sky just turns red, orange, you can kind of tell just from that. So, I'm just gonna leave, the last slide, Dan. I am gonna leave you with this, if you have any. This is, well, this was sort of my sum up, slide to sum up all of the things about PM 2.5. So if you have any questions, let me know, or I can answer them now, or when we go over to Lacey later, if you have questions then. So,
Okay, thanks, Odelle. Questions for Odelle?
I just have one quick